So an interface, what is that? What is that really? And usually when you hear that word, probably the first thing that you think about is this language construct in PHP, where you write interface and then the name of the interface and the curly braces. But that's really not what it's about at all. It's not about language constructs. And I think that's kind of a general thing with OOP, object-oriented programming, where we focus too much on the language constructs as opposed to the real concepts behind them. So when you're learning OOP, what's the first things you learn about? Well, you have a class, and then you have an object is an instance of a class, and then there's inheritance and visibility, and all of that crap that really doesn't matter. Because fundamentally, what it's really about is message passing. It's about objects that are like cells in an organism, and they're exchanging messages. They're sending messages to each other. So that's really what an interface is all about. A different term for it would be protocol. And I kind of like this term because we also use it for network protocols, which puts more emphasis on the actual communication. It's not invoking a procedure, it's sending a message. And that's kind of a different way of looking at things. So I think fundamentally, it's all about communication. So take Bob, for example. This is Bob. And Bob's really happy. He's walking down the street, runs into this really cute girl called Alice. So he says, hi. And then Alice responds, but he doesn't really understand because she's speaking in a different language. And you can also think of an interface as a language. So they're speaking different languages. They can't really communicate. So how do we solve this problem? How can we make both Bob and Alice really happy? Well, one solution to this would be to use a translator. So this guy knows both of the languages. And whenever they want to communicate, they just send a message to the translator. He translates it and passes it on. So the translator translates it and tells Bob, aloha. And Bob is happy. Yay. And so he sends the message back. And a different way that you could think about this is that these are objects, and they have different interfaces, and this translator is essentially just an adapter. So let's take a look at history. I really like this quote. If you watch the software industry backwards, it starts with kids flailing, ends with old guys solving impossible problems by thinking hard. And it's kind of exaggerating, of course, but I think there is some truth to it that we don't really know what we're doing. And I'm not saying that all of the old guys knew what they were doing back in the day, but if we do look at history, I think there's a lot we can gain from that. So you might recognize these two fine gentlemen. Who recognizes them? Anyone? A few? Two? So the guy in the red shirt is Mr. Dennis Ritchie, inventor of the C programming language. And he was working at Bell Labs in the 1970s. So what I want to do now is just go back to 1970 and see what they were doing. And the other guy, the guy in the white shirt and the strange glasses, that's Ken Thompson, creator of the B programming language, and basically the father of UNIX. So these guys were at Bell Labs creating UNIX and all of the tools around it. So here's another picture. Again, Dennis Ritchie, this time a bit older, longer beard. And the other guy next to him is a man called Doug McIlroy. So this was the tech lead back at Bell Labs. And he was more or less in charge of the entire UNIX operation, if you will. So what this guy did, well, for one, he had a really big nose. So that's one of the things he's known for. But what he did was put the pipe into Unix. He's the inventor of the Unix pipe, and he mandated that the Unix pipe be put into Unix. So now we have pipes. Yay. And there's this famous quote by him where he describes this Unix pipe as a universal interface. Because what it really is just a stream of text between two endpoints, and it just flows in one direction. So this is a UNIX pipe. You have two processes, and they're completely isolated. Each process is just running, doing its own thing, and they're not in any way connected apart from the UNIX pipe. And the only thing that you can do is send a message from the sending end into the receiving. So it's a unidirectional way of sending messages. And so we have all of these different Unix utilities, and you can really nicely just tack them together to build workflows of data transformations. So here's just a couple of examples of these utilities. This will be cat, just takes the input and spits it right back out. Then we have rev. It takes a string, reverses it, sends it back out. Grep takes a list, or a list of inputs, and filters out based on a certain pattern, or of course calce, which makes everything more cow-like. And this is really nice because each program is isolated and just does has one distinct responsibility, and you can tack them together without actually having to care about all of the details of how they're implemented. The only thing you care about is the interface. So you're just making a list of things and separating them by pipes. And the output of each preceding one is piped into the input of the next one. This is a program that finds the longest class names in a PHP project. So Unix pipes are great, but there's kind of a problem. And the problem is that a Unix pipe only works on a process. It only works on a single machine. And at some point, we might want to talk to other people. We might want to have some networking, talk to some other machine, send them some messages. So you can't use a Unix pipe for that. What you use for that instead is some sort of TCP or something. So you have a TCP port on both ends. You have a binding port on the other end, and then you have a connecting port where you just open the connection to them. But now we've got these two different worlds. We've got the TCP world, and we've got the pipe world. And they're kind of similar conceptually. They're both more or less streams of bytes or streams of text. But they're still kind of different. They're implemented in a different way. They're kind of different interfaces. So how can we do that? How can we bring this pipe world into TCP land? Well, there's a utility for that called netcat. And this is the netcat logo. So netcat looks basically like this. It has a pipe on one end, and it has a port on the other end. So it's almost like a portal gun that you can just aim at any machine and shoot a portal, and then you can just start throwing stuff into it. So that's one way that you could think about it. So this allows us to bridge the gap, because it adapts from one interface, a Unix pipe, to the other interface, the network. And now we can do something like this. So we have some network that we don't care about. It's just somewhere in the middle. It's some cloud thingy. And stuff goes in on one end and comes out on the other, and that's all we care about. So now we can do all of the nice things that we had with pipes, except we can do it over a network with other machines. But managing all of these connections can be kind of a pain, especially if you want to be a server. Well, then netcat just doesn't cut it, because it can only kind of really deal with one connection at a time. It exits after that connection is dropped, so then you need to do it in a while true loop, and then while it's restarting, then someone might be connecting right at that time, so he can't connect, and then he has to reconnect, and there's all of this stuff that you need to deal with as kind of a pain. So that's why they came out with xinetd, or inetd, which was then xinetd was the new version of it. So inetd is an internet daemon. It does more or less the same thing as netcat, but it manages all of this connection stuff for you. So this is more or less what it looks like. You have one binding port, and anyone can connect to it. and then it actually creates a new UNIX pipe for each connection. It creates a new process, and it hooks the TCP port up with the UNIX pipe. So then you can just specify any command, and whenever someone connects, it has a nice connection to whatever server command that is running. So this is pretty nice. And you have these nice declarative configuration files. So you just tell it, I want to define a service, give it a name, give it a port, give it a command, and that's more or less it. So let's do that. Let's make a fortune command that just does a nice fortune cookie message and spits that out to the user. So you just configure it, give it a name fortune, point it to a script. So we're going to write the script. And the script is just a little bash script, which has a fortune command piped into calc to make it look a bit nicer. And so from the remote end, you can now connect to this service. You've just written one configuration file, one bash script, and you're done. So now when we connect to this, this is basically what we get. You just get a nice little message, and after that, the connection is closed. So we already have a pretty useful service. But it's not that interesting yet, because it's not really processing any input. It's just doing something and spitting back output. It's like a static thing. So how about actually consuming input and doing something more interesting? So how about we expose calc itself, which is basically calc as a service. So what we can do is point this to the existing calc binary. Just point it to the actual calc command that we installed with a package manager. We don't even have to write a single line of code. We don't have to write a bash script. We can just point it to that, and we're done. So now, when you want to connect to it, you can just echo whatever, or have some output of another command, pipe that into netcat, and the other end will then receive whatever you sent it and return you something like this. So this is pretty nice. But it's still not that useful. I mean, we can do better. So what could we do with this? What could we do with this approach? Well, we could do anything. We could parse network protocols like this. We could, here's kind of a generic way that we can process input over the network. Just read some input, do some transformation, do some output. And with this model, we could implement network protocols. We could implement HTTP this way. We could make mail server. It really doesn't matter. And as a matter of fact, this is how the web used to work. This is how protocols used to work. This is how they were actually implemented. As actual bash scripts, or actual, Unix commands that would read the input as opposed to doing their own networking. So the web came along, and then they made this thing called CGI, which is the Common Gateway Interface, more like a gateway drug, that was basically a way of decoupling the responsibility of parsing HTTP from the responsibility of doing some application logic. So you have a parser that is separate. And this is more or less what it would look like. So you have inetd. And inetd is handling all of the networking. And you don't have to care about networking. So network is done. Now you just have Unix pipes. And for each connection, it creates one of these HTTPD web servers. So that one just passes HTTP, which is actually really hard. Because if you've ever looked at the eBNF in the HTTP spec, it looks like a simple protocol. It really isn't. So then you have this web server, does all of the parsing, and through CGI, it then invokes your application, your script, your CGI script. This is the output. So CGI is kind of slow. So they came out with FCGI, which is fast CGI, which is like CGI but faster. And this is more or less what it looks like. So the web server is now handling all of the networking itself, and this CGI, or the FCGI script, is also a networked thing. It also has a port and also talks over sockets. So we've replaced all of the pipes with sockets. Sockets are the new pipes. OK, so this is kind of the evolution that things went through. You have HTTP, then you have CGI, which kind of models HTTP in terms of environment variables, then PHP, which is kind of a hack on top of that, and a templating engine written in C or whatever it was. And then you have fast CGI. So they're all kind of doing the same thing. They kind of represent the same HTTP stuff. But then something interesting started happening, because we had all of these different languages, and they all started implementing their own in-language models of HTTP, which works kind of differently, because they model it in terms of language data structures. So we had that for all of these different languages. One of them Ruby, which the thing was called rack. This is more or less what rack looks like. You get an environment, which is just a hash map of all of those env vars, and you return a tuple of 3 elements: the status code, the headers, and the body. Then, what about PHP? Well, PHP never really needed that, because PHP had this thing called the SAPI, the server API. And the server API already does this. It already models all of these HTTP semantics inside of PHP. You have an abstraction layer that really is agnostic of the backend. So we have different implementations of this SAPI. It works with CGI. It works with HTTP with a built-in web server. It works with FCGI. And there's a couple more. It really doesn't matter. So the whole argument of having to abstract the backend, having to abstract the actual protocol handling, is irrelevant. We already have this kind of built-in in-language thing. And this is what the SAPI looks like, with the superglobals and echo and header and exit. Those are the ways that you interact with it from a script. So this brings us to HttpKernelInterface. And this is where things get a bit weird, because we have this SAPI around our PHP process. And then we have the PHP code, our own PHP code. And the SAPI already kind of does all this. So why do we have a kernel inside that does exactly the same thing? Silence. It just doesn't make any sense. And it's kind of like this. It's just stacking stuff on top, and it's almost falling off, because it just, I don't know, it's just so weird. Just a quick rant. I've heard so often that you should wrap your legacy code, whatever that means, in a kernel, and then you send in a request and you get out a response. Well, sorry, but that's not true, because if you have one single exit call hiding somewhere, it's not going to work. So why do we care about HTTP Foundation and HTTP kernel? And there's a couple of myths here. If you ask anyone why they should care, the first reason is going to be caching. You can do ESI, and we have a built-in cache, and it's so amazing. Well, sorry, but just use Varnish. I mean, it's going to be faster than implementing your own caching inside of PHP. So what is the other reason? Well, you can do functional tests. It's amazing, functional tests. Yeah, well, you can kind of do functional tests without that as well. And just as a proof of concept, I made this CGI HTTP kernel, which exposes the kernel interface, but actually uses CGI underlying. So this is more or less what it looks like. You interact with it as if it were a CGI, as if it were an HTTP kernel, but it actually does CGI under the hood. And what I didn't quite realize at first is that this is basically, well, that this is completely agnostic. Not only can you test any PHP script, you can test anything that implements CGI. So you could use this to test your Ruby code if you wanted to. And this is more or less how you use it. So you just point it to a directory, and that's it. Now, what's actually kind of nice is that we have all of this infrastructure around testing HTTP kernels. And we can use that. We can actually use all of the browser kit stuff from Symfony to test anything now, because you just plug in a different backend, and now you can test your Ruby code with the Symfony browser kit thing. So that's kind of nice. That's already maybe one reason why you would want to have an HTTP kernel thing. And just one side note here, it's kind of slow with the CGI thing, but we already know how to solve that problem. Just replace everything with sockets. Problem solved. OK, so that's not really the reason why we have HTTP kernel. I mean, where is the actual value? Why should you actually use it? Why should you rewrite your code to no longer use the built-in stuff in PHP? And I think the value lies in the fact that it models the request and the response in terms of values, in terms of these value objects that represent the request and represent the response. Because if you look at the S API, the API sucks. It's completely bollocks. You have these global things, global everything. I mean, we know that globals are bad. Come on. So this scopes everything locally. Instead of having everything global, instead of calling a function and praying that it won't just echo random crap into your page, you now actually have a way of knowing, OK, I'm going to get a response object, and I can actually look at it, and it's not just going to spit out some stuff into my page. So I think that is the reason why we should care about it, because it makes our code better. It scopes everything locally. But there's a few things that I didn't tell you about. First of all, FCGI has this thing called roles. An FCGI process can be one of these three roles. So it can either be an authorizer, a responder, or a filter. None of the web servers actually implement this, but it's in the spec, and I think it's conceptually quite interesting, because an authorizer is something that can accept or reject requests, and a filter takes the output of an existing response and spits something different out. So you can kind of mutate it, modify it in a way. So that's kind of neat, and actually it's almost like the HTTP kernel event. And another similar thing is this thing in rack, which I also didn't tell you about, which is rack middlewares. So rack middlewares allow you to wrap an existing rack application and do exactly this, either do something before the request or do something after. So what I'm proposing is bring this to HTTP kernel middlewares. So just imagine if there were an HTTP kernel or an implementation of the kernel interface that doesn't use the standard implementation, a different one. I mean, it's a crazy thought, right? I mean, who would do that? Well, actually, it's already happened. Laravel, for example, doesn't use the standard implementation. So they already can't use event listeners, which means if you're basing everything on event listeners, then that's not composable. That's not composable with Laravel. That's not composable with potential future implementations of this interface. So this is just one example. So here's an example of a middleware. This is a logger. What it does is it implements the interface. It decorates an instance of this interface, which means it takes an instance in the constructor, and then in the handle method, you can either do something before you delegate or after, but you just need to delegate at some point. So this allows you to do something before or after every request. And here's how you would use it. So you just wrap the application in one of those middlewares. But we already have that. If you look at Symfony, if you've ever used the HTTP cache, use Varnish, by the way, if you've ever used this, then it's exactly the same. It wraps an existing application. This already uses the same pattern. So, and that's actually not, shouldn't be a surprise, because it was initially ported from the rack HTTP cache. So it's already based on all of that stuff. So this is more or less where it's going, where you have an application and you just wrap some layers that are completely reusable, completely composable around it. So I'm just going to attach this name stack to this idea. It's not really a project in a sense. It's more giving a name to this because I don't really want to say HTTP kernel middlewares all the time. So just stack middlewares is a bit easier. So yeah, it's a different take on event listeners. The way that you write a stack middleware is these three rules: implement the interface, take an instance in the constructor, and in the handle method, delegate. That's pretty much all there is to it. There's a couple kind of standard middlewares that you can use, which are also proof of concepts, so you can look at how they're implemented and get some ideas for how to do your own. The URL map just allows you to take any kernel and mount it under a prefix. So you can take any application that starts at / and just say, I'm going to mount this under /blog. And so when you go to /blog, you get that. And it rewrites everything nicely. And then this session, which is also nice because lots of different frameworks that use the kernel interface actually have their own session implementation, whereas this one is completely reusable. So no longer do you have to have a Laravel session and the Silex session and the Symfony session, but you just have one and it wraps around nicely. Then this is a proof of concept that I did, just an authentication thing, which allows you to do Twitter auth and other stuff. One thing worth noting here is that there is a way for the outside layers to communicate unidirectionally with your application by using these request attributes. So if you have a no-auth token and the application itself might want to make some decisions based on that, you can just throw that in the attributes and they can, the attributes kind of populate through the layers. So completely composable in order to make this a bit more nice, because writing this new app thing kind of looks weird. So there's this builder thing, which makes it a bit nicer, where you just declare which middlewares you want, and then resolve once, and it does everything for you. There's a couple middlewares already existing. I think there's a lot of potential for more of them, because then they can be used between all frameworks instead of having to re-implement everything and have a Silex service provider and have a Symfony bundle and have all kinds of stuff doing all of the same, really. So I think there's really a lot of potential there. And yeah, go stack some middlewares. I guess that's it. Thanks.